Okay, good morning. We are going to continue with this course on optical engineering. Yesterday we looked at some important definitions. One was of aperture stop. So basically we looked at what are the optics that limit the cone of light traveling through the system, and in extension of that we looked at some planes which were arrived at from the aperture stop, namely the exit and the entrance pupil. In addition to learning about these elements or these planes, we also needed to know which rays to trace through the system, and we defined therefore two important rays. One was the chief ray and one was the axial ray. Okay, and the definition of these rays, they kind of interlinked with the definition of the aperture stop, because we say the chief ray goes through one part of the aperture stop, the axial ray will go through another part, and so on. So continuing that, or rather we ended the class yesterday looking at the exit pupil, which is the image of the aperture stop seen through all the elements after the aperture stop. So it's very clear from that definition, if you don't have any elements after the aperture stop itself will be the exit pupil. Okay, but given that there are elements, then you will find the location of the image and that becomes the exit plane. And we said 4 applications where you as a user are going to look into your system. The exit pupil must of course lie outside the entire system. Now say, what can you think would be different in an optical system that was being used in the daytime compared to an optical system that is going to be used at night? Let's say you had a night vision binoculars compared to binoculars you would use during daytime. What can you imagine you would have to do different in your design of optics? Is there a difference? Yes, there is a difference. Why is there a difference, or what is the difference? Okay, so larger aperture so that you get more light, but in terms of the exit plane, what can I say? Same principle, you said larger aperture, I must have a larger exit pupil, right? What happens to our eye when we are viewing something in bright light as opposed to viewing something when it's much darker or dimmer? The pupil of our eye changes. Do you know the range of sizes our pupil can vary through? Okay, so it can vary from about 2 millimeters. So under very bright conditions, the pupil of our eye will be about 2 millimeters, and it can go all the way up to a diameter of 8 millimeters if the lighting around goes down. Okay. That's the range for a human being. If you've seen a cat, you can see the cat's pupil can vary much larger. It's a remarkable change from a slit to a very large opening, which is why they have so much better vision. Well, one of the reasons why they have better vision at night time. Okay. For a human being, we're saying the pupil varies between 2 to 8 millimeters. So clearly, a binoculars or any system that is going to be used during night time as opposed to the daytime, the design must be such that the exit pupil matches the pupil size of the human, depending on the conditions in which they're using it. So you have to take that into account when you're doing your design, right? It's not enough to say the exit pupil must lie outside. Of course that's true, but its size also depends on what are the lighting conditions you're working under, because the human eye will respond to that and change according to that. Okay, so you need to take all these things into account when you're doing your design. Okay, so I haven't actually told you how do you find out the aperture stop. We did a nice definition and maybe the words were clear, maybe the words even weren't clear, but basically I gave you a definition of aperture stop. And in all the examples we looked at yesterday, we had very nicely one lens and one aperture. Very simple systems. But of course, your systems are not always going to be so simple. So how do you decide which of the elements in a system is actually the aperture stop? So I'm going a step further. I'm not going to go to 100 elements or 50 elements. Let's just take 2 elements with power. So in this example here, I have 2 lenses with power, of course, they're lenses, and in between that I have an aperture of opening 1 centimeter. Okay, so I have 3 elements in this system, and now I want to calculate which is the aperture stop. Now I can take a guess, given that the diameter of the lenses are much larger than the diameter of this aperture, it's quite likely that even in this case the aperture will turn out to be the aperture stop, right? But that need not be the case always. Keep that in mind. It depends upon the focal lengths, the positions, because it depends how the light is going to be bent and traveling through this system. Okay, so we'll use this example to calculate and find out which of these elements actually is the aperture stop of the system. So if you can draw this quickly, because I'll go to a new sheet where we'll actually do the calculations. I want you to have these numbers. It's not drawn to scale, and our goal is to calculate the aperture stop of this system comprising 2 lenses and 1 aperture. This phi here denotes the diameter of the lens. Okay, so it's that tells you that this distance is 6 centimeters for the first lens and it's 4 centimeters for the second lens. So that's to do with the physical size. So if you remember, we kept talking about the aperture stop as being the element that limits the cone of light that reaches the image plane. So I'm going to calculate aperture stop by calculating angles. Okay, I'm going to calculate the angle extended by each of these elements and find out which one has the smallest cone, which one has the smallest angle. So my method of calculating aperture stop is calculating angles. Okay, so in first calculation is I'm going to calculate the image of the second lens as seen through the first lens. Okay, so the object distance, and now this is where sign conventions are going to be very important. The object distance, can you tell me what is the object distance from your figure? Your second lens is the object now. Don't get confused that it's a lens. It is just now an object. You're treating it as an object. What is, and the lens you're imaging with is the lens L1, right? So what's the object distance? Minus 5 centimeters, right? Because the object is to the right of the lens. Now this is where another point which is slightly tricky. The focal length, yes, it is a convex lens, but I am working in image space. So I will not put down plus 9 centimeters. You are given the focal length as 9 centimeters. I will put down minus 9. I'm not going to write down the units as centimeters everywhere. Okay. So although it's a convex lens, we are working in image space, and by this sign convention I must take that fact into account by indicating a minus sign over here. Now we are using a very simple Gaussian lens formula, which is this. I want to find out the location of the image, so I can do this. So when I substitute minus 5 minus 9 minus 5 plus 9, I'm going to get 45 by 4. In other words, 11.25 centimeters. This is positive. Where does the image occur? It should not be surprising to us. It occurs on the same side as the object, because the focal length is 9 centimeters, but the object distance was 5 centimeters. The object is less than focal distance away. We have a virtual, erect, magnified image on the same side as the object. What's the object? Lens L2, right? Okay. But what we wanted to find out was the angle subtended by this image. So I haven't got there yet. I have only the location of the image. So this just tells me location. I still need to calculate the size of the image in order to get the angle subtended by the image. So, to get the size, I will use magnification, and magnification is m, which is minus v by u. So, this is minus 11.25, the object distance was minus 5, and so this becomes 2.25. We know it's magnified, now we know exactly how much it's magnified by, 2.25 times. This is equal to the image height by the object height. Again, you've been given the size of the object, that's the radius of that second lens. So, I can find the image height yi, it is 2.25 times the object height, and the lens had a diameter of, was it 6 centimeters or 4 centimeters, okay. So, then its radius is 2 centimeters, right. In other words, it's 4.5. Now I have all the information I need to calculate the cone of light. I want to calculate the cone subtended by this image, and I know I must, for new aperture stop definition says as seen by a point in the object space. So, to make this, to make it consistent, I will do every calculation from the same point in object space, and I will make it easy and say we will choose the point from which I am making all these observations. Let me just choose the object location. Okay. So, the object in our example, in our overall system, the object was located 12 centimeters away from the first lens. So, the angle I need to find out is, I have an object here, I now say I have 12 centimeters to some point, and then I have another 11.25 centimeters to this image of the first element, and I have 4.5 centimeters. This is the angle subtended by the image, right. So, I am interested in theta, which is tan inverse of 4.5 by 12 plus 11.25. Okay, and this turns out to be 10.95 degrees. So, the cone of rays that the aperture, the size of that second lens would allow through the system, taking into account bending, is 10.95 degrees. Okay. So, I have one piece of information. Okay. But that is only this element. I now need to do the second element, and I used up all my space here. Okay. So, I now need to calculate the second one, right. For the second one, let us just do the angle subtended by the lens L1 directly. Now, for L1, there are no other imaging elements before it. So, I do not have to calculate any image now. I can directly calculate the angle, and what will I get? This dimension is the nothing but the size or the radius of the lens. What was that? It was 3, right? This was 3. And the object point is 12 centimeters away. So, theta over here, let us call this theta 2, let us call this theta 1. Theta 2 is going to be tan inverse of 3 by 12, which is equal to 14 degrees. So, if I did not have any other element in this system, I would say now very clearly the second lens is the aperture stop of the system. It subtends a smaller angle, and that itself is interesting because the diameter of the first lens is larger, but because the rays bend, its diameter directly isn't playing a role in the maximum cone of light that makes it through the system. So if I didn't have the third aperture, I could at this point say the second lens is the aperture stop of the system. Okay, but there is another element. Now that element has no power, but again, when I am calculating aperture stop, I don't have to worry about that. I will now use that element as the object, image it through lens L1 and carry out exactly the same procedure that I carried out in this case here. Okay. So, I am not going to carry out that entire procedure, it is going to be exactly the same as what we have done in the first step. We can just maybe write out our parameters. U in this case is -3 because the aperture is 3 centimeters away from lens L1. We are using lens L1, so the focal length is -10. We are in image space, that is why the negative sign comes, although it is a convex lens, right? And again I will calculate the location of image, the size of the image, and I will find out the angle subtended by the image, and that will turn out to be 0.75 is this dimension. This is 12 plus 4.5, this is theta 3. So, theta 3 is tan inverse of 0.75 by 16.5, and this works out to 2.6 degrees. So, when I look at this simple system, 3 elements, the element that limits the cone of light that reaches the image plane is the aperture stop. In this case, we kind of guessed that at the beginning because its diameter was so much smaller than the other elements. But we now have mathematical proof that the aperture that lies between these two lenses is actually the aperture stop of this system. Okay. So, this is how you calculate aperture stop. So, this is the logic, and the point that you should be getting now is it isn't the diameter alone that controls the angle of rays that go through, because this is an optical system. It has elements with power, that means it has elements that bend rays. It's quite possible that rays get bent and are able to make it through the system or are not able to make it through the system, depending on how they are bent through the system, and you have to take that bending into account. And that doing this calculation where you find the image, because the image is a result of how light has bent and traveled through the system, right? And therefore that gives us a way of calculating the location of the aperture stop, or which of the elements is actually the aperture stop.